Okay for recording. Thank you very much for your kind introduction, Andreas. Today I will talk about CBETA, that's the Cornell BNL ERL test accelerator. It is the first 4-turn ERL that recovers the energy in SRF cavities, and it has many other interesting features, like for example, it is largely based on permanent magnets. And I will cover a few things here. The abstract of the talk that you can find on the OWLE webpage emphasizes that the efficiency, the power efficiency, is an important topic that we research with CBETA. And that is because we believe that power efficiency will be a more and more important paradigm in large accelerators. The power needs of large colliders, for example, become so high that you really have to look carefully into energy savings. The energy savings that we pursue are energy recovery in itself is a large saving. Of course, tell you more about that later. Superconducting cavities provide energy saving, and permanent magnets provide energy savings over electromagnets. This accelerator is called the Cornell BNL ERL test accelerator because it was designed, constructed and commissioned in a very strong collaboration with Brookhaven National Lab at the Cornell campus. And so I give credit to these great collaborators. It was not only a collaboration with Brookhaven, but we had people come to our commissioning shifts from 8 different laboratories from US, Europe, and Japan. And also this international collaboration was very important and really pleasurable. The permanent magnets are arranged in a very special way. It's called the fixed field alternate gradient lattice, where we have a large energy aperture of nearly a factor of 4 and send 7 beams simultaneously through one beam pipe. That will be another important feature that I'll cover in this talk. And then I will go to applications that can be potential uses for CBETA and other ERLs. Now, let's first go back to basic types of accelerators. They fall mostly in 3 categories. One is the synchrotron, another one is the storage ring, and the third is the LINAC. And of course, I'm brushing very broad strokes here, but synchrotrons are great for fixed target experiments. They can accelerate in a circle to very high energy, but they typically have very low currents because they shoot on a fixed target, so the beam energy is lost, and they have relatively large size. Storage rings are like synchrotrons, except you accelerate once and then they store the particles for millions of turns, and therefore they can have high energy, but they also can have high current because they recycle the particles millions times over for every turn. So the storage rings are great for high energy, high current, and then you often use them for colliders. LINACs, on the other hand, have other advantages. They shoot the beam straight onto a fixed target, so they typically have moderate energies. They have small currents typically because you throw the beam away after they have hit a target or have been used for some experiment. And so you have these applications of different types of accelerators, especially LINACs, having low current, but they can have very bright bunches because the beams don't have to be bent in circles, so they can have very well preserved bunch properties. And storage rings, high energy and high currents, but typically the bunches are not as well preserved because you have to store them for millions of turns and you have to bend them around curves. Now, this leads me to one further type of accelerators, and that's the energy recovery LINAC. The energy recovery LINAC is an accelerator where you simultaneously get very bright bunches, well preserved because they will not be bent around curves, and at the same time you get high currents. And how that works, I'll tell you in the next few slides. The idea is pretty old. It came up in 1965 in a paper from Maury Tigner from Cornell. And the first idea looked like this. It's the so-called push-pull ERL, where you have 2 superconducting cavities. You accelerate a beam through one cavity and another beam through the other cavity. You build a collider experiment in the middle, and then you decelerate the right beam in the left cavity and the left beam in the right cavity, giving the beam energy back to the SRF cavities where it can be used to accelerate new beam. That was a rather nifty idea. It took decades to realize anything like that, but one reason typically ERLs don't look like that is that you could get beam forces in the cavities when these linears get very long. Another even nice idea I kind of like is this one, where you accelerate in one cavity, you bend the beam back onto itself and collide here, and then recover in the same cavity. Pump the beam energy into the same cavity we have previously accelerated it. This old idea is basically how ERLs work today. You use the same cavities to accelerate beam, and then you bend them back and in the same direction decelerate the beam again. The reason this works so well is that you have a LINAC where you accelerate beam, and because it's a straight path, the beam properties can be preserved very well. You can get beam that has the high quality of a LINAC beam, but because you take the energy back and recapture the energy, you can also have very high beam currents. So that's therefore the fourth type of accelerator that I want to talk about today, the energy recovery LINACs. It's a linear accelerator. It accelerates and it decelerates to capture the energy of the spent beam, like a LINAC, but without the power limit of on the beam current. So you can have much higher beam current than in normal LINAC, because the spent beam itself provides the power. Of course, the loss rates have to be limited, because whichever electron you lose or whichever particle you lose after acceleration, you cannot get its energy back. One application of these ERLs is that you can build colliders with higher luminosity. How does that work? So first of all, you have a beam that can be brighter than in a ring. So the emittance can be smaller. You can focus the beam more tightly, so you can have higher interaction rates. Usually in a storage ring, you cannot make the interaction rates as high as you might want to by focusing the beam more tightly, because then the beam force becomes so high that the particles will be lost in millions of turns. Whereas every particle in the ERL gets only accelerated once and then decelerated once, so that you don't have to worry about this beam force so much for millions of turns. So you can drive the luminosity high. So one application of ERLs is to build colliders with higher luminosity. But there are many other applications, and I will go through those. But first, let's get to the ERL that we built at Cornell. So here is an outline of what has been designed and constructed. We start with an electron source. It's a DC source, photoemitter source that we built at Cornell. So you have a laser beam that shoots onto a cathode crystal. Photoelectric effect produces electrons, and a DC field sucks off these electrons to accelerate them into a superconducting injection LINAC. In our case, we accelerate to 6 MeV. That beam then gets optimized to be as bright as possible. The design is 100 milliamp. We have achieved 75 milliamp, which incidentally is a world record for the current of photoemitter sources. And here we have a diagnostics line where we measure the 60 phase space density of that beam, optimize it to be very close to the theoretical limit. And then we build a mirror image injector. We just mirror image these magnets over to this side, so that we then get these high beam qualities in the linear accelerator, where we cannot measure them anymore, but because of the mirror image, we know they are there. And then we accelerate them, and we actually accelerate them 4 times. We come back, accelerate them again, accelerate 4 times, and then decelerate 4 times to get the energy back. Because we accelerate 4 times, there will be 4 different energies in something we call the spreader region. The 4 different energies get separated to different beam lines, where they get separately optimized for time of flight, for their optics, and for their orbit. After that, they get recombined into one joint, section where permanent magnets are arranged in only one beam pipe. So the 4 different energies go through the same beam pipe. That works because this beam pipe has this fixed field alternating gradient optics with an energy aperture of nearly a factor of 4. So all these 4 different energies from 42 MeV to 150 MeV can be stored in this joint beam pipe. And that's where the permanent magnets are placed. And after that, the beam gets energy recovered, it gets decelerated 4 times, comes back to 6 MeV where it stops. So continuously we inject, accelerate, decelerate, and dump the beam, so that a DC current at 150 MeV is available for experiments. Because we send 4 beam energies through the same beam pipe, we have in one beam pipe these different orbits and different optics that breathe in every of the periodic cells, and we have to store the beam simultaneously, measure the orbit simultaneously, and correct the orbit simultaneously with corrector coils through which all these 4 different energies fly. So you can imagine that's a bit of a challenge. The collaboration between Cornell and Brookhaven has been very active and productive and already long-standing. The project started really in 2005 when we started to get funding for a DC source at Cornell University. And then Cornell designed a hard X-ray light source, 5 GB light source based on energy recovery LINAC. We produced a detailed design report, which still has very valuable information. That light source was not built, but all the components that we prototyped for that project, we now use to build this energy recovery LINAC, that is CBETA. We wrote a white paper together with Brookhaven on that project already in 2014. We got funding for it in 2016. We wrote a detailed design report, that's the front page, in 17. That you can get copies of. And then we tested most critical components in 18. And in 19, we first operated a 1-turn ERL where we just accelerate 1 time, decelerate 1 time, and measure the degree of energy recovery. And then at the very end of 19, we managed to build the first 4-turn energy recovery LINAC with all these 4 spreaders and 4 recombiners on the other side. The components that came from this first light source project contributed a big part. This was the gun, the main injector, and the main LINAC and the dump. So this was tested separately, and then we joined this collaboration with Brookhaven. Brookhaven took over all this permanent magnet construction and design and the expertise for the fixed field alternating gradient. So it was a very productive collaboration where both sides brought in very important components. The power of this beam is very high. I'm showing here dots for all the ERL projects that have been envisioned in the world, and we are really at the very high power limit. And we, of course, we are the only ones who got this 4-turn ERL to work, or any multi-turn ERL to work so far. But I show this picture for 2 reasons. One is the power that we designed for 6 megawatt is very close to the high power that an electron cooler for the electron-ion collider needs, 15 megawatt. So we can test many features for this electron cooler. In fact, the experts for these coolers all say that the only way you can produce that beam is an energy recovery LINAC. So we are a test bed for that system, for example. Another important thing I want to show is that all currently active projects for energy recovery LINACs actually joined a collaboration with us and helped us in our commissioning effort. And most of them sent people to spend time with us during commissioning. So much credit to those institutions. Building this energy recovery LINAC started, as I said, with the gun through the SIF cryo modules, and we had to build much of that ourselves from scratch. Here, just pictures of the injector cryo module that we built in our clean room. We installed the cold couplers, the helium vessels for the cavities were built in-house. Inside the cavities, we built the cavities starting from niobium sheet metal. We electron beam welded, we stamped the sheet metal, we electron beam welded everything. Had to be built in-house. Higher order mode absorbers next to every cavity suck out unbounded modes out of the cavity. All that was constructed. So we got the first cryo module. We had to build a second cryo module about 10 meters long, the main LINAC cryo module for the ERL. That's the first cryo module that was optimized specifically for energy recovery LINAC operation. That means it was optimized for very high beam currents, but for very low RF power needs, because that's what's special about energy recovery LINACs. You get very high currents, but you don't need to pump in much power because the power comes from the decelerated beam. Our space is very tight, so we built the cold mass in 2 sections in our clean room. We then had a helium gas return pipe in a stand, put the 2 half cold masses together in a local clean room, and then push them on rails into a long vacuum tank that then built the cryo module. We had a experimental room available that's about 20 by 30 meters in size. It was completely filled with lab equipment, but we were allowed to use it, clean it out, renovate it. That's the cryo module. The accelerator was then installed here in the geometry. The DC gun, the injector linac accelerates in the main linac. We return through these permanent magnets 4 times for acceleration and for deceleration. And the return loop itself was built with enormous help from Brookhaven here, Brookhaven staff assembling one of the sections. You see that these magnets are all built from permanent magnets by this little ring. The permanent magnets are of the Halbach type, where you build little sections of permanent magnet material and orient their magnetization so that they build a cosine 2 theta quadrupole around the beam pipe and superimpose the cosine theta dipole in our case. So this builds the strong magnetic field. The coils around only produce a 2% corrector magnet. So the corrector magnet actually is much larger than the main permanent magnet that guides and focuses the beam itself. We have about 200 such magnets. The FFA, fixed field alternate gradient optics, is a photo-like optics that has a photo with just 2 magnets, focusing and defocusing, and they repeat. The focusing strength is so strong that the focal length is much shorter than the bending radius, which means you get adiabatic conversion of the periodic orbit and the periodic optics in a bend arc, periodically or adiabatically changing to the periodic solutions in a straight section. That's a very powerful feature of these strong focusing FFA lattices, that you can adiabatically change direction and the periodic optics and orbits change independent of energy smoothly and adiabatically over to new solutions. The total accelerator looks like this. So if you look at Dejan, who is listening to this talk, you will see in his background is exactly this accelerator. The gun is back here. The injector linac is also back here. It injects beam into the main linac, and then we return 4 times through the permanent magnet sections. The red lines are cooling lines because permanent magnet material changes about 10 to the minus 3 for 1 degree Celsius. So you need to cool the magnet material, and we put the permanent magnets in aluminum sleeves and water cooled them. Other things you see here is, of course, it's a superconducting linac. So we have helium pump skids. We operate at 1.8 K. These are the pump skids. You see that we need quite a lot of power in the injector linac, where the energy is not recovered. We just inject. These glystrons feed this injector linac. The power for the main linac, because its energy recovery is much smaller, here we have only 5 kilowatt per cavity, and that is provided through couplers from solid state power supplies behind this concrete wall. So that was the idea. We got funding from an agency in New York State, and we had a very fixed set of milestones, and we clocked through these milestones and achieved at the end every single milestone, and all on time. Actually finished a little bit before schedule. So having this project laid out for only 3.5 years and then finished on time was really quite an achievement. Before I go step by step through what we achieved, I actually want to give you the conclusion already, so you can then remember what we did when I go through the specific details. We built the DC source. We operated at high current, 75 milliamp, more than needed for this ERL. We build a detailed phase space diagnostics where we can actually measure the 6D phase space X prime, Y prime, energy and time to build the density distributions and optimize them. We tested this gun for high bunch charges up to 2 nanocoulomb. We then built an SRF injector that sends beam into the ERL. We operated that with the same beam current to more energy than we need. For the ERL, we operated only at 6 MeV. Then we built the main ERL SRF linac. It has 6 cavities, each cavity nearly 1 meter long, and it's the first linac optimized for energy recovery operation. We then operated it as a 1-turn ERL and checked that every single cavity at least energy recovers 99.4%. And we then also operated as a 4-turn ERL. We found many interesting effects in beam dynamics. For example, microbunching is one that is worth much more analysis, and I'll show some of that later. We did these energy recovery studies with relatively small current because we did not want to damaged equipment. The 1-turn operation, we limited to 70 microamp, and the 4-turn operation, where we lost quite a bit of beam at the very end, we limited to only 1 nanoamp. Interesting is that in the FA return loop, even so this complicated system that has 7 beams simultaneously in it, we hardly lost any beam. That system worked very reliably, and beam loss was restricted to other areas that I can show you later. Here a few things. For example, the DC source operated very stably at 65 milliamp for a long time, short time for 75 milliamp. The cathode lifetime was very good, so that we could, even at that high current, live with the cathode for about a week. The beam brightness achieved world records. So for 100 milliamp, we would need a bunch charge of 80 picocolor, and we achieved basically the theoretically limited brightness with that beam, which was a world record. In many sections along the beam line, we checked beam distribution versus simulation, and we came to understand the space charge dominated dynamics very well, so that we could actually get a simulation and measurement matched very well along the beam line. Also, beam size and emittances got measured, and where we can measure them, they agree or verify that we understand our beam dynamics rather well. To do that, you need to simulate in a lot of detail. For example, you need to start by measuring your laser distribution on the cathode. So that's actually laser shining on the cathode, and map that with the quantum efficiency map, so you know at what place how many electrons come out. When you take the measurement and the simulation that starts right on the cathodes with the accurate electron density distribution, then on the subsequent screens you can get simulation and measurement agree very well, and that goes down at different screens along the beamline. The simulations keep matching rather well. And so that's for the beam distribution. We have similar systems where we look at orbits and compare orbits online between simulation and measurement. This turned out to be very powerful. We call it CBETA V, the virtual CBETA, which is an accelerator model that always runs in parallel to the actual running accelerator and uses the same epic screens, so that when you for example, change an orbit in the accelerator, then simultaneously this virtual machine changes its orbit too, and you can plot them both simultaneously. For example, here you change a corrector coil, which will make an orbit excursion, and you see the simulated orbit excursion together with the measurement, and you see that they match very well in the horizontal or here in the vertical. So that beam then gets sent through a LINAC. The LINAC is made out of 7-cell cavities. So here you see some of these 7-cell elliptical cavities. And one issue is that we need to make sure that the field in these cavities is very stable, while the 7 different beams go through these cavities. And so field stabilization becomes very important. In energy recovery LINACs, the quality factor of the cavities, the loaded quality factor, is extremely high, close to 10 to the 8 in our case. And it is so high because you recapture the energy in cavities, and of course you benefit from recapturing this energy only if the energy can be stored there for a long time, and that's what the quality factor indicates. The quality factor says how many oscillations can the energy be stored there, 10 to the 8 in our case. But that also means that the resonance frequency gets extremely narrow when the Q is very high. And so you need to regulate the resonance frequency of the cavity very well. And that is hard when there's microphonics, when the cavities oscillate, either here transversely or vertically, through to microphonic vibration in the environment. Then it's very hard to regulate because the frequency of the cavity then oscillates back and forth when its geometry changes. And keeping the field maximal when you are not always at the same frequency in the resonance curve is very hard, needs very delicate optimization. So to get that under control, we had a project where we identified many vibration sources and then built active feedback systems to make the RF regulate correctly, and also passive feedback systems to minimize the microphonics vibrations. Here are sources. So there was a PhD student who identified a long list of possible sources. For example, there are water pumps, there are warm compressors, there are connections, waveguides from the power sources to the cavity, and all of these can transport vibrations. A very important feature was that these long waveguides can vibrate freely. So after we fixed them at certain places, we reduced the microphonics enormously. Another important feature were cryogenic thermoacoustic oscillations. For example, you have valves in these cavities that come from the outside. Here, there's outside a valve stem that connects to the cold inside. And of course, while the outside is room temperature, some of the heat transport goes out and you get freezing out in this region. So you see there's a strong thermal gradient from the outside to the inside. And that can basically create little thunderstorms in the connecting pipes. And these produce whistling sounds. These, I call them thunderstorms, produce whistling sounds that can put vibrations on the cavities. We put sleeves around these stems to avoid that gases oscillate back and forth. And that also eliminated many of the vibrations. So after all, we initially had rather large peak detuning of the 6 different cavities. And after all these measures of minimizing vibrations and active feedback, we got that each cavity had below 23 hertz detuning out of 1.3 gigahertz, so tiny detuning. The tolerance was 54 hertz, and so we had all cavities under these tolerances and could operate the cavities and accelerate the beam to the energy that we needed. The person who did that is now freshly baked Dr. Nilanjan Banerjee, and you can get much more details in his PhD thesis. So with that, the cavities were stabilized and the beam went accelerating and decelerating one time. That was the very first beam, summer 19, where we had an energy recovery link at Cornell for the very first time after having proposed it here by Merit-Tigne in 1965. So now we wanted to know how much energy recovery does every cavity actually get, because that's at the end the benefit of this concept, that you can get beam accelerated to high energy even though you don't provide power into any of the cavities. The only reason you do have to connect some power to the cavities is because you have to regulate the RF field under the presence of microphonics. Other than that, you don't need any power to accelerate the beam because the power comes back from the decelerated beam. So to measure whether every cavity actually has that feature, we accelerated the beam in the first 3 cavities and immediately decelerated in the last 3 cavities to then stop the beam in the beam stop at 6 MeV. To accelerate the beam in the first 3 cavities as a function of beam current, you need an increasing amount of power that you pump through the coupler into the cavity. And so the slope of the power against the current tells you how much power from the power sources you have to invest to get the beam accelerated. So this slope tells you how much power needs to be sent into the beam to get it accelerated. The same happens if you then decelerate the beam in the other cavities. You get the power back, and the slope is basically the same. Again, this slope tells you how much power needs to be put into the input coupler to get the beam accelerated. With energy recovery, I said we should not need any power to get the beam accelerated. So as a function of current for the energy recovery case, there is indeed no power. The beam current goes up, but no more power goes into the couplers of the cavity. Well, if you look at the slope exactly, there is of course a tiny amount of power that goes in, and that's for 2 reasons. One is some particles get lost before the energy can be recaptured. That would produce a little slope. And the other one is that the phasing may be incorrect. So you might be accelerating at a higher field than you decelerate because the phase might have wandered a little bit. So we found that the transmission was at least 99.6%, so no more than 0.4% of the beam was lost. And we found that the phasing problem caused that the energy recovery efficiency just from phasing, if there had not been any beam loss, is better than 99.8%. And that's true for every single cavity, not only for energy recovery in total. That's of course very important to show that this principle works. So that was our first turn. Now we want to move to a 4-turn energy recovery. And that's where we need these 4 spreader lines to separate the beam. That is not easy because the spreaders and recombiners need about also 200 magnets. These are electromagnets, and they are closed, very closely spaced. Because it's a very compact accelerator, the magnets get very compactly close together. For example, here you have one beam pipe for one of the beam energies, and right next to it, the other one with a bending magnet that separates the beam energies. And here's a corrector coil. And we got stray fields from one pipe to the other, so that if we corrected that beam, for example, we also steered the other beam a little bit, and we need to disentangle that. So that made operation with 4 beams much more complicated than with 1 beam. But nevertheless, directly on Christmas 19, we got the very first 4-turn energy recovered beam. That's the first beam spot. And we could measure the current in all these 4 orbits. So here you see how over 4 times accelerating, so 1 times accelerating, 2 times, 3 times, 4 times accelerating, and 4 times decelerating. The LINAC is in the gap. 1 times, 2 times, 3 times, 4 times decelerating. We get this 4-turn energy recovery LINAC to work. And then at the very end, of course, there's a beam stop with the image that I just showed. And we found that in the first 7 turns, the blue are beam loss monitors. So our BPMs can measure beam loss. These are beam loss monitors in the return loop in this permanent magnet region. So we see that in the first, second, third, and up to 6 pass through the interaction region, we get in total about 10% beam loss. But then at the very last time, when we go back into the last turn, we get a large beam loss that we did not manage to avoid. In fact, it was, I'll show you in a second where exactly this beam loss happened. But you also see that in the permanent magnet return loops themselves, we hardly get any beam loss. Within the uncertainty, the beam is basically constant, and the beam loss happens always between the permanent magnet arcs. The permanent magnet arcs themselves were extremely stable. We measured the orbit in these arcs. And these are the orbits of all 7 beams that are simultaneous in the beam pipe, but you could measure them all separately. And you see we come in with 42 MeV, then we accelerate, accelerate, accelerate. That's 4 times acceleration, and then we decelerate, decelerate, decelerate. So we get 7 beams, and afterwards, after the last deceleration, we send the beam into the beam stop. This is the region where the return loop is bent, so the different energies have different orbits. This is the straight section where all energies go straight through. We get the adiabatic change of the closed orbit to the center. That's this adiabatic feature that when we slowly bend from curved region to straight region, the closed orbit automatically, without any corrector coils, follows its new periodic solution. We like that so much that we put up a t-shirt, and that's what made us all proud of this achievement. The orbit got corrected in all 7 beams simultaneously. This is vertical orbits. They're pulled apart for different energies, so you can see them, but the orbit got corrected for each different energies for 7 beams simultaneously. Important is also longitudinal phase space, that we correct the return time. So we have a measurement outside the BPM right in front of the LINAC, where we can measure at what time every beam returns, and it has to return at the right time to get the correct phase of the RF acceleration and deceleration. And theoretically, we computed what the optimal phase is. That's the circle, and then we measured and got the beams quite accurately into these phases. On average, we found that we need at least 2 degrees accuracy to get the beam into 4-turn energy recovery mode. So interesting is that this time of flight includes the different flight times you need in this FFA optics in the permanent magnet region. Different energies get bent differently, so they have different time of flights. And the fact that we got these time of flights right shows already that even in this permanent magnet section with the energy aperture of nearly 4, we do understand the beam dynamics rather well. This set of measurements shows it even better. The FFA region has photo lattices, so always 2 quadrupoles together make a photo, and so they have a periodic phase advance from photo to photo, and that depends on energy. And we simulated this periodic phase advance, including the fringe fields, including the effect of the corrector coils and their magnet core. And we then compared that to measurements, and you see in the arc section and straight section, they're slightly different, but the measurements are smack on to theory, which showed us that we understand that region very well, which also explains why we had so little beam losses in that region. The beam losses depend a lot on the detailed phase-space dynamics, and the phase-space dynamics is tricky for electron bunches that are short and have high charge, especially because coherent synchrotron radiation of the back of the bunch can shine onto the front of the bunch and make very detailed coherent effects. We studied in simulations in a lot of detail this coherent synchrotron radiation, and you see how the interplay of the waves that the beam shines onto itself together with time of flight terms produces micro bunching effects, and these stripes in the beam distribution that get worse and worse for higher bunch charges and kind of rip the beam apart. You see the energy spread of the bunch gets larger and larger and self-induced by this radiation onto itself. Simulating this is pretty tricky, and there was a PhD student, Wilhelm Lu, who got his PhD partly on this topic for the ERL by simulating in a lot of detail and accurately checking out convergence criteria to make sure we can trust these simulations. And indeed, we don't only simulate that, we see these effects in the accelerator. We see when you measure the electron beam longitudinally that we get micro bunching developed in the beam. Here you see it as a function of bunch charge. We start at very low bunch charge, bunch looks nice and pristine. And that's on a screen in a dispersive section so that the horizontal corresponds to the longitudinal bunch coordinate. And you see that for increasing bunch charge, we get this broadening of the energy spread, and we get these micro bunches developed in the beam. All these measurements were, of course, needed a big team. Here I show pictures of people mostly from Cornell and Brookhaven that collaborate a lot. So this was why we set up the first spreader line, people from both groups. This is in Brookhaven, when the first chain of permanent magnets was constructed. But as I said, we had collaborators of 8 labs from international institutions. From the US, it was Brookhaven, Cornell, and JLab. And then we had labs from Europe and KK from Japan. And they all sent people to the control room, helped us write reports, and of course helped us commissioning and run our shifts. And it is still a very nice collaboration that helps with energy recovery efforts. Now let me talk a bit about applications for CBETA itself and energy recovery Linux in general. There has been a EIC hadron cooling workshop a while ago, which looked into options for using electron beams to cool the hadron beam in the EIC. And that is needed to increase the luminosity of the EIC. And basically the conclusion of that workshop is you need an energy recovery LINAC to make this work. So this here I took directly from the summary slide, which said so research needs for ERLs for the EIC are there. High currents need to be tested in injectors because you need about 100 milliamps, which incidentally is our design criteria for one-turn operation. You need to do design work for CSR, exactly the effect that we also looked into. And you need to investigate things like the beam halo, because beam halo in intense beams can easily damage equipment. Beam loading, the beam that goes in the direction of RF control that we, of course, had to investigate a lot also. Beam breakup instability is an effect where the higher order modes in the cavity shake the beam, and the shaking beam comes back after a turn and can exactly excite those higher order modes, leaving an exponential instability. We studied that a lot theoretically, but that needs experimental investigation. And then there are transients in the RF fields when you turn the beam on or when you turn the beam off because of beam loss. Also, that needs to be studied to start off the operation. CBETA is able to do all these analyses. So with that, let me tell you some of the achievements that I mentioned already. So CBETA has fulfilled all milestones of our construction contract in time, in the 3.5 years period. CBETA found many important operational topics that will be important for every ERL, for example, for ERLs that do hard-run cooling. ERLs are needed for hard-run cooling, and they are needed because otherwise the highest luminosity cannot be achieved. And CBETA is a test bed for these ERLs. We can not only test the high currents, but several issues that I will mention on the next slide. But beyond that, CBETA is an accelerator physics treasure trove that can study many effects that are important in other accelerators as well. So not only effects that are important for the ERC hard-run cooling, but CBETA can address topics that are important for many other potential new accelerator applications. And these include medical isotope production, computer chip lithography, high energy physics experiments, and so on. I'll go through some of those in the next slides. A big achievement I also find is that CBETA has pulled this international community together, has built a very strong collaboration between the university and a national lab. And that's also something that will be beneficial to the ERL community in the future. So back to hard-run cooling to tell you a bit more what we plan to help with the CBETA technology and the CBETA experience. One is the hard-run cooler for the ERC needs, guess what, 150 MeV, that's our energy. It needs about 1 nanocoulomb, which is in the region what we study, and it needs about 100 to 120 milliamp, and we went close to that and can therefore study all these parameter ranges. Beam loading, beam breakup instability, and RF transients, all effects that have to do with SRF, are important for this high current ERL for the ERC and can be studied at CBETA. In the injector, the DC source can be studied for that energy range and for that current region already. We have seen microstructure that will be a danger for the ERC, and we can study it. It's especially a danger because the beam has to be very smooth. Phase-space distribution has to be very smooth to be able to do hard-run cooling. Hard-run cooling works by superimposing the electron beam with the hard-run beam. The electron beam then picks up longitudinal microbunching from the proton beam, and that microbunching is amplified to correct the microbunching in the proton beam, basically. So you cannot have microbunching in the electron beam already ahead of time, or that would swamp the signal that you want to use from the proton beam for its cooling. Then in the ERL loop itself, we can look at transport effects, at halo effects, beam loss, and CSR. And we can also look into whether CSR can be shielded by sending the beam through a narrow vacuum chamber where the CSR, the coherent radiation, does not fit into the vacuum pipe and get shielded by the vacuum pipe. Another application, though, is what I would like to mention, and that's mostly because it's the highest energy application envisioned for ERL so far, is that there is a ERL-based concept for the future circular collider, for the E+ E- version. And there you have a ring that is supposed to collide E+ E- beams at high energy, for example, up to 250 and 250 GeV. But the standard design is a storage ring, but there's a design out there now that uses an energy recovery linac in that ring where you have a source, you store at 2 GeV, and then you accelerate in 2 linac sections, accelerate again and again and again. There are different designs. One of them has six paths. You accelerate 6 times to get to 250 MeV, and then you decelerate again and energy recover. So you have these linacs which in energy recover, and you can increase the collision rate. In fact, for the same amount of synchronous radiation, which happens to be in the standard design 100 megawatt synchronous radiation for the beam, you can get 10 times the luminosity if you use an ERL. Or if you want to get the same luminosity, you can reduce the synchronous radiation to only 1/10. And I said already, the paradigm of saving power will become more and more important in large accelerators. So having only 1/10 the synchronous radiation loss, of course, is a very important feature for the same luminosity. The reason we get the same luminosity, or the reason that for the same luminosity we can get only much less synchronous radiation is twofold. One is we can live with much smaller beam current because we can focus the beam more. Why can we focus the beam more? Because the bunches collide only once. so they can survive a much larger disruption, a much larger beam force in the collision, that a beam that you need to store millions of turns could not survive. But if you only collide once for each bunch, you can survive a much larger disruption. And therefore, you need less current for the same luminosity. That's one reason. The other reason is that even the highest energy path around the loop does not have quite the same energy as the collision energy, because before you collide, you accelerate in another turn. So in one of the designs, this is about 35 MeV or 37 MeV, 37 GeV acceleration in the LINAC. So you have significantly less energy in the arc than the top energy. And since the synchronous radiation goes with the fourth power of the energy, that is a significant effect as well. So not quite the highest energy in the loop, plus lower current reduces the synchronous radiation by a very large factor for the same luminosity. Now, other applications are, for example, just from the injector region that we have optimized a lot in CBETA, we can study ultra-fast electron diffraction in that dedicated setup. That setup is especially nice for ultra-fast electron diffraction because we have a lot of parameters. We send the beam from the gun through this injector LINAC, which has 5 cavities and therefore 5 independent voltages and phases that we can use to optimize the beam for ultra-fast electron diffraction in the MeV range. Medical isotope production, the DC source and the injector LINAC can produce high current as well as high power input in the beam in the injector LINAC. So if you use several injector LINACs, you can produce very high beam powers that you could use, for example, to produce isotopes. There are other ideas for medical isotope production, for example, sending an energy recovered beam through a gas target where you then produce isotopes is one application. Microchip production uses EUV beams. You can produce those in FELs, but you need very high beam currents. Again, you can use an ERL for these beam currents. There is the idea of compact Harks X-ray sources, where you use the ERL high current beam with very high brightness and make a Compton backscattering source from sending the electron beam against photons from a high power laser. You can do that effect to gamma rays and actually produce a gamma ray source for nuclear physics, again by using photons to scatter off the high brightness ERL electron beam. You can also use a gas jet target to send the electron beam with high density and high current for fixed target collisions in nuclear physics experiments. All these are applications of ERLs in general and also specifically for CBETA. Then there are applications of the FFA permanent magnet technology that we prototyped. One is that we have now this experience with a permanent magnet beam line that has a very large energy aperture. That is ideal for cancer therapy gantries, where you need to scan the energy of the beam to scan the penetration of the particles into the cancer of the patient. And since we have a very high energy, large energy beam line with our FFA lattice, you can scan the energy in the beam will always go through, and it will be adiabatically transported through curves of this gantry. Radiation damage studies, especially for permanent magnet materials, is something we can do and have already done to some extent with CBETA. And then the FFAs could also be used for building small synchrotrons based on permanent magnets, and therefore synchrotrons with very low energy consumption. So much to what spin-offs and applications of CBETA technology can be. And with that, I would like to open to your questions.